Welcome you all to my lecture series. As we are discussing about soil water, today we shall discuss about the soil water movement. Soil water movement. How the movement of water takes place in soil. We shall discuss this. Before going for the discussion of soil water, we should know some fundamental principles that govern the fluid flow. In general physics, we normally use the word fluid, but in soil we use the word like soil water, soil moisture. This is very simple. Fundamental, we can say fluid flow. Okay, fundamental principles of fluid flow. In this way, we will discuss first about Bernoulli's theorem, or you can say equation. He gave that equation for non-viscous and incompressible liquid. Okay, if you see the figure, I am not going for the derivation part because these are fundamental. We have already known through our lower classes. We will just use the applied part. If water is flowing this way, we can say this will be straight line. I am drawing schematic diagram. This is not important actually, the diagram. Just to make understand, I am doing this. If I am choosing a point 1 here and choosing a point 2 here, he said that at both the points, the energy acquired by the water or fluid will be equal. What are the energies? One is your potential energy, another is your gravitational energy, kinetic energy, gravitational, or we can say elevation. Because of elevation, the energy it acquires, you can say elevation energy. Another one is your kinetic energy, and this is constant. But in our soil terms, if we see, we will normally actually in our soil terms, we will use this energy as head unit. I have discussed already the potential energy in terms of your weight, in terms of your volume, in terms of your mass, known as soil water potential, your chemical potential, hydraulic head. So we will normally use this energy in head units because the unit was centimeter, and for convenience purpose the calculations will be easy and also easy will be for us to understand. So in terms of head unit, we can say the potential energy, okay, or we can say here the pressure head, that is P rho density of water into G. This is called as pressure head. And elevation energy or elevation head, we can say Z. This is your due to the elevation or gravitation. Okay. Kinetic energy your half m v square. Okay. This is constant, or we can say it is the total energy. Okay, total head. But in soil, for our convenience, how we use this equation or theorem, that it is, I have already told, this is the pressure head, and this Z is your gravitational, or we can say what, gravitational or elevation. Just remember here the gravitational, we will use this term. And in case of soil, we normally neglect the kinetic energy. We have already discussed. We can neglect this kinetic energy. For pressure head, I can write HP. For gravitation, already J is written. So in soil, we from this theorem, we will for ourselves conclude that the pressure head plus your gravitational head is your total head difference. Just remember, from this theorem, we have concluded for our soil that the pressure head plus your gravitational head is equal to your total head potential, or this is the total energy by which water will move. Now coming to another important principle, or we can say law, that is your Poiseuille's law. We all heard of that law. We also some might be knowing this law also. Poiseuille's law. If the spelling mistake is there, we should go for that. Not a big problem. Now consider this is a cylindrical pipe. Okay. This is a cylindrical pipe. The flow is occurring actually in a streamline way, and here the fluid is viscous. Viscous flow. Okay. So this is the radius. This is the thickness L. And this way we say that Q, volume of water flowing, okay, for unit time, that is the unit centimeter cube per hour, is your pi r to the power 4 by 8 into viscosity into delta P by your L. That from here we can say your volume of water flowing is directly proportional to the fourth power of radius. Okay, and directly proportional to also what? Your pressure difference. If more here is a point 1, here is a point 2. Okay, if the more pressure is here and here is the less pressure, water pressure, the movement will happen from higher pressure to lower pressure. This is your delta P and R. Normally in soil we have already known that the macropores compared to the micropores release more water, or movement of water will be more. So simply this is the applicability in our soil. You can see. Okay, r to the power 4. This is r is radius of your pore. Simply we can analogous to the radius of your pore, and it is inversely proportional to your viscosity as well as your length of the soil volume. We already know if the more the viscous the liquid or the fluid, the less will be its volume of flow. This is very simple. From this, we actually confirm that the size of the pore, if the more, the flow will be more. Volume of flow for unit time will be more. Now, in this way, another fundamental principle we must know before going derivation of the soil water movement is your Reynolds number. Reynolds number, Re. This Reynolds number is nothing but simply we can say this Re is the ratio of your inertial forces of flow to viscosity. This is very simple. Okay, but in our case, what we will use if the Re value is less than 2000. Okay, in a straight pipe, consider a straight pipe, then the flow will be laminar. Okay, but in our soil, if this Reynolds number value is less than 1, in case of our soil, the flow will be laminar. So you have been now question, what is laminar, what is turbulent. So if you see, laminar means the flow occurring in a straight line way. We can say flow is occurring in a straight line way and they are parallel to each other. The consider there is a rock structure now Bernoulli. The flow will be obstructed, so the flow becomes turbulent. Here the flow is laminar. Okay. In normally what we observe, in normally soil the flow is always laminar because the pore size is very small and the path is actually takes in tortuous way. So we normally in soil observe laminar flow. That's why the Darcy Law will derive later. We'll see how the laminar flow is. If the value is more than equals to 1, then that will be your turbulent flow. Also, in case of your turbulent flow, what will dominate? If the inertial process will be dominant, okay, and in your laminar flow, they will be affected by your viscosity, because we know it is inversely proportional to viscosity. If more the viscosity, the laminar flow will be there. So, in case the property of water is viscous, that's why the flow is also laminar. And another point, before we go for this water movement, we know saturated water flow and unsaturated water flow. I'm just discussing. You must be knowing, I think, in saturated condition what happens? All the pores are filled by water. So there will be water movement will be, hydraulic conductivity will be more. We'll see what is hydraulic conductivity. And here actually in saturated case we will derive the equation using Darcy Law. And in unsaturated soil, we will actually derive this unsaturated water movement using Buckingham Darcy Law. Okay, that's much you remember. This Darcy Law actually will derive in saturated condition. Okay, and another point in saturated soil we can say the flow is actually continuous, but in unsaturated soil the flow is uncontinuous. Now we'll come to another important point, that is your soil water movement in saturated condition. We'll first study in saturated condition, then we'll go for the unsaturated condition. If we see saturated condition, normally there are two conditions here. One is your soil column will be horizontal, another way soil column will be vertical. There is also inclinational, but we will discuss only two. It will be easy for you to understand. First, we take horizontal soil column. Saturated soil water movement in a horizontal soil column. See, this is a soil column. This is its inflow and this is its outflow. This is a soil column. Okay. If we say thickness of the soil column is L and the area of this soil column is your this A, or you can say A, area A. Now we will be maintaining the saturated condition. So we are maintaining this hydraulic head, saturated hydraulic head. Okay. This way we can draw. Now here you can say, you can write this way. This is hydraulic head draw. Think what? Hydraulic head draw. Very simple. And this is your, from this to this is inflow. This is inflow, where the water will go to your soil column. So I can write this HI. And here the outflow. We can write HO, because I already told you, we are measuring all these potential terms in hydraulic head terms. Not complicated. We can someone also go for the potential, maximum potential or total potential. Like this way we can calculate. But for our convenience are easy to understand, and all these laws are also given in head units. So we are using simply the potential energy for unit weight. It is hydraulic head. So if you see, this is your influent. So the water pressure or hydraulic head of water pressure head is maintained up to this point inflow end, we can say H. And if I am taking the reference point here at ground level, this is your reference level. We can take arbitrarily anywhere. Okay, and it is a saturated condition, so inflow end and outflow end will be on same line, and the distance due to elevation we can write Z. We have already discussed the total energy, or we can say in head terms, total potential head from that Bernoulli equation. It is the nothing but the sum of your pressure head and your gravitational head because of due to elevation. Okay. Now, in terms of HI at inflow end, the head difference will be your, what is your delta H? Delta H is your inflow end minus outflow end. The water pressure head will calculate what head will calculate at inflow end and outflow end. The differentiate will go in total potential water head. Okay. Now at HI, I can say the pressure head is H and gravitational head is your Z. Very simple. And at outflow end, and this is outflow end, we can say the pressure of water is now your 0, and because of this elevation, here is also the gravitational head is also there. If you calculate the total head difference, HI minus H0 will get H. Remember this point, we will use that in Darcy equation. Okay, in case of your vertical saturated condition, if this is your soil column, this is your soil column, we have to maintain the constant head, water pressure head, this is your soil column. As I have discussed there, this will be your thickness and this will be area. And one point you always remember, in case of those principles or simple fundamental rules or theorems, we have discussed in a microscopic level. But in soil actually, the pores are not in a straight line. There are dead ends, there are necks. Okay, the flow, that's why the flow is affected. The flow becomes in soil actually, the flow becomes tortuous. Okay, the path is not a straight line path. So, in case of whatever the calculation we will do in case of soil, here also, in case of Darcy Law, we will use it in a macroscopic way. So, what is the macroscopic way? This macroscopic way, we consider, as I have told you, that one point, second point in those theorems, but here we consider this whole soil column as a unit, and the calculation will be done, not at a single point, this point, just at inflow end and outflow end, considering this whole soil column. So that's why this is very important point. So all those principles we have studied, fundamental principles, this will be applied in a macroscopic way. Okay, you must remember this point. Now, this is, I can say HI, inflow end, this is outflow end, where water will be outflow. Now, from here to inflow end, there will be water pressure head. There will be water pressure H if I am taking the reference at outflow. This is arbitrary, you can take reference point anywhere. The value of your Z, or you can say H will be, the value of elevation will be changed, but the total calculation will not change. Okay, you can take here, okay, the Z, if you see, this is your elevation. This is your elevation, or we can say gravitational head, and the value of your gravitational head at outflow end is 0, and here it is, we can say A. This is very simple. Just try to understand. This will be very easy for you to remember. Most of the students I have seen get confused in this saturated water movement of water flow or Darcy Law. Okay. Now, at age I, if I calculate the hydraulic air at influent, what will be pressure will be your H, and your what will be your what that will be your H, and at outflowing I have already said this total pressure head is a function of only your pressure head and your gravitational head. Already discussed. Here we can say your Z is your elevation is 0 and this is your X. Sorry, this is also 0. So at influent this becomes also 0. So here the delta H becomes H plus L. This is your hydraulic air. And this is your horizontal saturated condition. This is your vertical. And in here we can express it as in hydraulic gradient term. Hydraulic gradient. Simply delta H we divide it with the length of the soil column L, it will become hydraulic gradient. Hydraulic gradient. This is actually the force which will govern the water movement. I can term it as I. Here also we can say the hydraulic gradient is your H plus L by L. Just remember, in case of your horizontal, that is H by L, hydraulic air by length of the soil column. Here H plus L by L. So here what we do done? The gravitation is neglected. The gravitational head is neglected. This is the most important thing you must know. In case of horizontal saturated flow, we neglected the gravitational head. So if we have a horizontal soil column, instead of going for this, we can directly also calculate the head. How? With inflow we will use the piezometer. Here we will calculate the head, and here we will calculate also water head, pressure head. Okay? Because gravitational head is neglected, so here we calculate pressure head. Here we calculate pressure head. Just differentiate, we will calculate the hydraulic gradient. This is very simple. And now we will derive the main ingredient we can say in this soil water movement, which is your Darcy law. For deriving this Darcy law, we have studied all this. So this is the most important one, which is Darcy law. Darcy is actually a French engineer. What he said, he simply said the flux is directly proportional to your hydraulic gradient. I can write hydraulic gradient I, or you better convenience you can write this. Okay, and this Q is your flux. It is also can be said that volume of water flowing per unit area per unit time. This volume is in unit centimeter cube. This is centimeter square. This P is your second hour. Okay. So in this way, if you go for Q, the unit will be centimeter per second. This is very simple. And as there is proportionality, we can assign a proportionality constant value K into delta H by L, or you can say hydraulic gradient. Okay, this K is actually very important. This is hydraulic conductivity. Okay, the negative sign is actually assigned here. Why? This negative sign is because of the head drop. I have discussed this head drop. This negative sign is actually assigned. Now, if you want to define also this, you can define in many ways. You can say the volume of water flowing. The Darcy law states that volume of water flowing per unit area per unit time is directly proportional to your hydraulic gradient and inversely proportional to your length of the soil column. You can say this. You can say the flux of water flowing through this soil column is directly proportional to the hydraulic gradient. Or we can say that this flux or volume of water flowing per unit area per unit time is equal to the multiplication of your hydraulic conductivity and your hydraulic gradient. In this way we define. Also from here we have derived how this horizontal soil condition and your vertical soil condition it is derived. So we can write this hydraulic gradient H by L for what? Horizontal soil. Okay, and if the soil column is horizontal, we can write this equation. If the vertical flow is happening, we can write H plus L by L. Now you get to my point. Okay. Now we will discuss about some assumptions. Every law has some assumptions and limitations. Here the Darcy Law assumptions actually we have already discussed. First assumption you can say assumptions. First assumption you can say we have neglected the kinetic energy. We have discussed many times why kinetic energy is neglected. And second point you can say the density should remain constant. Viscosity should remain constant. Okay. But this normally does not happen because with increasing temperature the density value actually changes. And mass density should remain constant. Mass density of water should remain constant. Another important one is the flow should be laminar. For laminar flow, what is the condition? The Reynolds number should be less than 1. If we come to limitations, I will draw a graph to understand this. Here I am taking your flux. We have already seen what is the unit of flux? Centimeter per hour. Okay. And just remember, in Darcy Law, we have calculated we have seen the flux, hydraulic conductivity, hydraulic gradient. What are the units are there? In hydraulic gradient, we are taking head upon your length of the soil column both in centimeter. So this is actually hydraulic gradient is your unit length. Just remember, this type of questions actually asked. What is the unit of hydraulic conductivity? K, we have given that hydraulic conductivity in terms of K. So K is your equal to your flux. The unit of K is your unit of, we will use the unit of flux. Centimeter per second or hour can write here. Here we are drawing because Q versus I, hydraulic gradient. And their slope will be your hydraulic gradient. This is very simple. We see this type of graph actually generates. What happens? Consider this is your fine textured soil. Fine textured soil. This is your loamy soil. And this is your post texture soil. Post texture soil. First condition you see for fine texture soil, or rather I am writing here clay soil. We have already discussed in plasticity to actually if you are applying the hydraulic gradient, the flow should happen. But if the clay soil is there, to make this flow to happen, okay, we need some threshold value, or rather I can say yield value. So this behaves what? This behaves like where there is yield value. We have discussed this behaves as Bingham liquid. This behaves as Bingham liquid. And in case of your loamy soil, where the flow is, I can say this is laminar flow. Okay, this flow is laminar. This behaves as Newtonian fluid. Newtonian fluid. And in case of your post texture soil, we can see the pore diameter is more as compared to your here. So here sandy soil, I can write the Reynolds number actually exceeds with critical velocity. Okay, your critical velocity will be so high that Reynolds number will exceed more than 1 or equals to 1. So this will be the limitations. This is mainly observed. The flow will be now here will be turbulent. We have already said the Darcy Law is valid for laminar flow. Now we can see two conditions where the laminar flow is not happening. Okay, these are the limitations. Now, if you want to calculate this hydraulic conductivity, very simple. In large condition, the constant head permeameter method is used. I am not writing to write down that constant head permeameter method is used for sandy soil. Okay, and for your constant head permeameter method is used for your sandy soil, and your falling head permeameter method is used for your clay soil. How these calculations will be done, we will discuss in this practical class. Otherwise, the class will be very lengthy. Now we discuss about hydraulic conductivity because this is very important. If we see some factors affecting hydraulic conductivity, one is your texture. Let's again draw this Q versus ICAR to observe this. You can say this type of curve form. This is and the equation. The slope of this line is your hydraulic conductivity K. This is for sandy soil. This is for loam, and this is for clay soil. We can clearly see the hydraulic conductivity in case of sandy soil at permanent at a hydraulic gradient is higher as compared to your loamy soil, as compared to your clay soil. This is very simple. This type of questions actually are. You just understand the concept here, so that it will be easier for you to remember. Then coming to structure, we know the spheroidal structure will be showing the hydraulic conductivity highest. This will be followed by your prismatic and block-like structures, and the lowest hydraulic conductivity will be seen in your platy type of soil structure. And another one is your compaction. If more compaction is there, your hydraulic conductivity value will be low. Very simple. If more the organic matter content, then there will be hydraulic conductivity more. Very simple. If the presence of sodium is there, this will cause dispersion. If the sodium quantity increase, the hydraulic conductivity will be decreased. These are some factors. Along with hydraulic conductivity, most often we see some words like intrinsic permeability, and your fluidity like terms are used. Okay, so we will discuss here. You don't get confused. Actually, this hydraulic conductivity is function of both intrinsic permeability. I am writing with K gas. This is A. Function of your intrinsic permeability and fluidity. Okay, actually, what is hydraulic conductivity? Simply, we can say the ability of soil to allow the water movement. Simple. And this K gas is your property of soil only. What are the properties of soil? Like your pore diameter, all these things will be included in your property of soil. So, what are the properties of fluid then? Fluid property are density, gravitation and viscosity. If the more the density, the more will be water movement. If more the viscosity of fluid is there, then the water movement will be less. And in fluidic terms, we can say simply the ability of water to move through the soil. Very simple. Here we will say the ability of soil to allow water movement. Okay, Okay, here we say ability of the water to move through the soil. Very simple. If the viscosity is higher, okay, the fluidity will be lower. We have normally seen this in case of temperate region. What happens in temperate region? The temperature is very low. Okay, so viscosity actually does increase. That's why the flow velocity decreases. And in case of your tropical soil, the density is actually very high, very low. The viscosity is very low because of increasing temperature. So that will be effect in fluidity. The more fluid flow will be observed. And we have seen that equation. Sometimes it is written as this way. This is minus k into hydraulic head drop x. Don't confuse, this is also a Darcy Law equation, but this is actually normally in 3-dimensional way. We will observe like as we are discussing about hydraulic conductivity, I have already told you that this flux, in case of if we want to show this Darcy Law in 3-dimensional way, we can see this flux is your product of your hydraulic conductivity in energy terms and potential terms and your hydraulic head drop. Okay, if you see how I have done this figure, you can say in 3 axis this hydraulic movement may happen. In x axis, y axis and your z axis. If the soil is, if your hydraulic conductivity is homogeneous, that means this will be uniform throughout the soil. Okay, and if you see it is isotopic, means this is a soil, this is identical one. We can say if this is isotopic, then at this point, 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 all the directions, the hydraulic conductivity will be your equal value. But in normally what happens, they are not isotopic and they are not homogeneous. They may be anisotropic. That means from one point to another point there will be difference in hydraulic conductivity. So that's why we can say anisotropic condition may be created, will be there. And another case we can say this is not uniform throughout the soil. This also changes from one point to another point. Okay. So if that's why 4 conditions or 4 cases we can say appears. Okay. This is actually not explained in your this simple textbook. This is given in Daniel Millen book. This is very important concept. I think you must need to know how the value of hydraulic conductivity actually decreases in 3 dimensions. So we can say if this homogeneous and isotropic, there will be single value of the hydraulic conductivity. Okay. You can say K equals to Ky. This is identical soil. Okay. This soil and this soil we are comparing. K is equal to your Kh star, or given for star, Ky. Now you can observe here, if this is isotropic from one point to another point, at X point, Y point, Z point, everywhere there will be your hydraulic conductivity will be similar. As well as in another soil, there will be also the value of Kx, Y, that K star, K2, Y, K, Y star, K, Z star. This will be your equal. But normally what happens, there are various conditions that appears in soil. If the soil is, the hydraulic conductivity value is homogeneous and anisotropic. Anisotropic means this K will not be your equals to Ky, not equals to your Kz. This is very simple. Okay. In this way, actually there will be 3 values of hydraulic conductivity possible. Okay, just remember these memory based things, try to understand here. And if the soil is inhomogeneous and isotropic, the value of K will be your 2. Okay. And if normally we observe the soil in this way, there will be various K values. The value of K will be your 6. Okay. Now, if you see in unsaturated soil, we have already up to now what we have discussed in saturated condition. Now, if we want to study the water movement in unsaturated condition or unsaturated water flow, as I said. Okay, what happens? actually we have expressed all our units in saturated condition in terms of potential unit. But simply here, the extending this Darcy's law, we can write it is this hydraulic conductivity function of volumetric water content. Simply just write how this derived. This is also given in textbook. This is little bit difficult, but I'm not normally not asked in exam. So that's why I'm not going for derivation class. Also the class will be get lengthy. Just remember the point here, and we can write this way. Like Darcy's law, just change your hydraulic conductivity value, where in saturated condition we are expressing it in energy terms. Here just express it in volumetric water content. Volumetric water content. This we have discussed what is volumetric water content. Your gravimetric water content into your soil density. How we have calculated. But you can say volume of water by total volume of soil. Like that way we calculated volumetric water content. So the question now arises, why, and this equation actually is called as Buckingham-Darcy equation. Like your Darcy law, you can write all these equations, but just remember the hydraulic conductivity values will be expressed in your volumetric water content. Now the soil, as we have seen in saturated soil, the water flow was a continuous process. But in case of your unsaturated soil, actually this is not continuous because of presence of air. We already discussed hysteresis. You have observed how the input effect and the contact angle effect, all these affecting the drying and the wetting curve. You can compare here also. Why is oxygen this volumetric water content instead of energy terms? Okay, this is very difficult way to understand, but you just remember these points. This will be easier for you to understand. If we are taking in terms of volumetric water content, we can see we are neglecting the effect of hysteresis. Okay, and in a volumetric way, we are considering all the soil volume. Okay, so that's why we prefer this question asked in exam. Why in unsaturated soil, in terms of hydraulic conductivity, instead of potential terms, we take volumetric water content basis. You just remember, in volumetric content, we are actually taking whole soil, and in potential terms, the effects of hysteresis, all these will be avoided. And we can say, in terms of energy, the air water interface of contact angle was studied. This is not covering your whole soil, but in volumetric water content, the entire volumetric water content, entire geometry of soil is considered. These are the 2 to 3 points. You just remember unsaturated water content. Okay. Another scientist, we can say his name was Richard. He gave also an equation which is also applicable in your unsaturated condition. I am not going for its derivation parts, and you just remember this type of question, this type of things. These are the memory-based questions you will ask. Here, partial pressure difference of d theta by dt. We can see in unsaturated soil already the hydraulic conductivity, all these things are expressed in where that volumetric water content. Okay, not in terms of potential. In your saturated hydraulic conductivity measurement, but we have taken the hydraulic head which is similar to your potential energy per unit weight, or we can say in terms of potential. Okay, but here we are taking, instead of potential, we are taking volumetric water content. Just remember, this is the Richard's equation. We can say this is one dimensional. This equation is one dimensional, and he also further extend this equation in terms of your soil water diffusivity. Soil water diffusivity term. You can just follow this equation. If we want to know then what is soil water diffusivity. This soil water diffusivity d theta Okay, is simply we can say K theta. K theta is your unsaturated hydraulic conductivity. Unsaturated hydraulic conductivity. And your C theta. What is C theta? C theta you can say specific or differential water capacity. Okay, so now the question arises then how we get this C theta now. C theta already we have derived, like I have done that soil moisture characteristics form. One side I have taken your volumetric water content, other side we have taken metric potential value or metric suction value. So this is the slope of this. Actually we can say the specific water capacity or differential water capacity. Now it is very simple and clear. Can say the metric potential by theta, volumetric water capacity.